Okay, so now in case 3, I am moving the regulator to 1.75. I'm maintaining the locations of the regulator at 1.75 meter, which is same as case 2, but with the additional setting of the R and X value, so that I am regulating the voltage drop at the end of the feeder. So the regulating point, right? So I said in case 3, move the regulating point to the end of the feeder. So SRP now is at the end of the feeder instead of SRP equals to S1. So now we need to have some sort of R and X setting. So these are given to us, okay? These are given to us. So the RA is the resistance, of the regulator. XA is the inductance of the regulator, and this is the another reactance of the regulator due to the dimensions of the cable. All right. So these three informations are given to you. Okay, but it's not. I obtained this information from somewhere else, and it's not given in the descriptions. But let's say that these are given to you, right? RA, XA, and XZ. All right, these three are given to you. Even in your assignment or in your test or in the exam later, these three information will be given to you. All right, and then these three informations is not enough for us, right? We need to obtain what we call essentially the line resistance and also the line inductance. Okay, notice here I put RL and XL, right? So because we only have one type of resistance, so therefore RL is equals to RA is equal to 0.386. But not this, right? The XL, the inductance, we have to get the total line inductance, okay, which is this plus this. So XA plus XD equals to 0.6611. So now we have this, but we need to know what is the effective inductance and the effective resistance, because our regulator is located at 1.75 meter and our regulating point is at 10 meter. Therefore, we are only regulating 8.25 meter of voltage drop. So the same concept as in the case 2 just now, the equation, you take the total length minus the locations of the regulator, L minus S divided by 2. All right. The why this is the equation, right? But why they divide by 2 is due to a concept similar to uniform voltage drop. Multiply with the XL. All right. If you want to calculate X effective, and you get X effective as this, and the same goes with the R effective, right? You get this. And remember the current transformer and the potential transformer ratio that we obtained previously, not obtained but given to us previously in this table. Yes. Now this come in handy, right? So the current transformer and the potential transformer ratio that I'm using is this one, because we are assuming that the regulator size, right, the single phase regulator size is 100 kVA. So 100 kVA is the most similar to 114, therefore we use these two values. So the way to use this table is that if you are asked to use, if you are given the regulator size of, let's say, 30, then you will use this ratio. Now that we are given the regulator size, the single phase regulator size as 100, therefore we use this value. All right. Let me see whether it's given to us or not. The size of whether it's mentioned or not, the size of the regulator. Not mentioned anyway, it's okay. But I can tell you, the size of the regulator that we're considering, let's assume that it's 100 kVA for single phase of it, right? Therefore, we use CT and PT as such, right? The ratio. So to get the X setting, you get CT divided PT multiply X effective, and the same goes to the R setting. And you do this, you plug in the value and you get this. So the X setting is this, and the R setting is this, okay, ohm per meter. And these two values, okay, are the X setting and the R setting that the LDC need to perform, all right, in order to get regulations down, to get the regulations that we want down the end of the feeder, which is 8.25 meter later. Okay, so this is the X and R setting that we need. So we're going to see how we are going to use this later on. So this equation will be involved, right?